Hey, what's up, guys? This is Chung here. So today, let's take a look at LeetCode problem number 887, super ag job. So this one is a very classic, problem, in terms of DP. So basically, you're given like a kx, and then you're given like building floors with n floor from 1 to n, right? So I mean, each ag is identical, right? I mean, basically, all the ags have the same hardness, right? And then if an egg breaks, right, and then you cannot use it again. So, and our goal is to use this kind of k eggs to find out there's a floor f, right, such that any egg dropped at a floor higher than f will break, and any egg dropped at or below floor f will not break. And basically, on each move, you can take an egg and drop at any floor. And our goal is to find this f and with the minimum number of drops. And this f is unknown. It could be at floor 0, or it could be at floor n, right? So but we want to make sure the minimum number of moves that we need to make so that we can find that f, right? So which means that since the f is unknown, so when we try to find this doing our algorithm, we should always assume the worst case scenario, right? Then that's going to be a certainty, right? So with this certainty, it means that we always need to assume the worst case scenario. So we have some examples here, but this thing are not very useful, So to solve this problem, so we need to. I think first thing first, we need to somehow understand how this thing works, right? So let's say I think it's a good idea to start with some base cases. Let's say we only have one egg, right? If we only have one egg, and we have n floor, right? We have n floors. How can we find the f? This floor, right? This floor f within this n floors, given like only one egg, and assuming the worst case scenario, right? Since we only have one egg, so the only way we can find this f is to try to drop this egg from the first floor to the nth floor, right? So which means that if at the ones, basically we have to drop it from the lowest floor to the highest floor so that we can make sure we can find that floor, right? I mean with this one egg, because let's say this f equals to 20, right? Assuming this n is 30, right? N is 30, f is 20. So if we try to drop it from the floor 1, the first floor, and then we try it from 1, 2, 3 until 20, right? And then when we drop again at 21, right, this egg breaks, right? And then we know 20 will be our final answer, right? So so basically that's going to be the scenarios, right? The base case, right? Assuming we only have one x left, right? So which means that the moves we need with one egg to find the floor in the nth floor will be equals to n, right? Assuming the worst case scenario, right? We're assuming the f is equal to 30 in this case, right? Then we need 30 drops to find this n here. So that's the very the basic case, right? But how about if we have two eggs, right? So what if we have two eggs? So I mean, with two eggs, we have one egg that we can drop at any location, right? Because let's say we have two eggs. Basically, let's say we pick case floor to drop the first egg, right? If we pick the case floor to drop the the first egg, right? So we have basically we have two options here, right? Either the eggs breaks or didn't break, or didn't break. Okay. So if the egg breaks at the kth floor, so what does it mean? It means that the f, right? The f is in a 1 to k minus 1, right? If it's in 1 to k minus 1, okay, and then what's gonna left? So if you guys remember, so now we only have one egg left because the first egg broke, right? So then we only have one egg. So with one egg, with this one k minus 1 floor, how many moves we need, right? We need a k minus 1 move in this case, right? Okay, so the second case is that what if the egg didn't break, right? So if the egg didn't break, it means that the eggs are in the I'm sorry, not eggs, the f is in what? F is in the uh, k plus 1 k plus 1 to n, right? Assuming we have nth floor in total, right? Then this one need how many moves this one needs? Basically, it needs n minus k minus 1, right? Assuming that we only have one x left. So which means that we'll need to use that one egg to check this k plus 1 to n floor, right? So for that one, we also have to drop this egg from k plus 1, k plus 2 until n. That's going to be a total moves, right? We need to check for the case of didn't break. And since we're assuming we want to make sure we can find the f here, so which means that we will basically do a maximum of the breaks. I'll use the b and then not break among those two things here, right? Because the breaks we have one moves we need to make, and with didn't break we have another one, another move we need to make. And since we need to assume the worst case scenario, that's why we're gonna do the maximum of the break and not break, right? And since we are choosing this case floor, right? Assuming we are like, let's say, assuming we have nth floor, right? We want to check. Basically, we can choose this choose k become to 1 to n, right? We can choose any floors so that we can have like a either break or not break values, and among all this kind of case scenarios, we want to get the minimum of those two, right? Of using k equals to 1 to n. That's basically gonna be our strategy to calculate this minimum. Basically, it's like a minimum of maximum values here, right? So, and this is, I'm only assuming trying to emulate the 2x cases, right? So let's try to generalize these things with like kx, right? So similarly at the 2x here, right? Let's assume, assuming we have dp knn, right? So this thing dp knn means that with kx and with kx and we have n floors, we want to check the number of floors, right? The number of floors we want to check what's going to be the minimum numbers of moves that we can find this f with certainty, right? So like I said, so this thing's gonna be the minimum of the dp of maximum, okay, maximum of dp. Let's assume we pick the pick floor we already have k and n. Let's say we pick floor m. We pick m's floor to drop the case egg, right? So if this case egg broke at this m's floor, then we have dp we have k minus 1 x left, and then how many floors we need to check? We need to check m minus 1, right? Because if it breaks, then we know the f is within this m minus 1 floors, right? And then if this egg didn't break, right, we're gonna have like what? We need to check the k. We have kx left, and then the floor number will be n minus m, right? And then we also need to do a plus 1, because this 1 means that the current drop, right? It's gonna be 1. So this part is kind of easy to understand, but the second part, right? Actually, so this one n minus 1 means that from m plus 1 to n basically. That's gonna be the total floors we want to check here. Since we're only considering the numbers of floors we want to check here, so we don't care if it's a lower floor or a higher floors. So it will be the same, right, when it comes to this DP definitions, because the definition of DP means that with this number of floors, with this case number of eggs, right? So we should have the same result. Yeah, so I think that's going to be the very first approach here. Okay, and so let's try to code that things, right? So with DP here, right, I mean, since we're getting the minimum, so I'll be initialize that everything with some system max size, and then so we have n plus 1, right, and then for this thing in range k plus 1. Okay, so I think there are like some base cases we need to check, we need to set. So let's say if with 0x, when k is equal to 0, right? When k is equal to 0, with 0x, how many floors we can check? Of course, it's 0, right? So which means that in range n in range of n plus 1, I'm using this n here. So we're gonna have dp 0, right? N, right, equals to 0. This thing means that with 0x, there, of course, we can check 0 floors, right? And then how about another base case that I think that we have already covered is if we have one egg, right? So if we have one egg and we want to check nth floor, the moves we need to make is n. Like I said, because we need to check from the lowest floor to the highest floor, which is exactly the number of n. Okay, so that's the first corner case. And second corner case is that basically if if we have 0 floors, right? I mean, that's obviously k plus 1, right? If we have 0 floors, of course that's going to be another 0, right? Because we need 0 moves, k of 0, right? And then it's also a 0. Then the rest will be then let's try to implement the main logic. So we have range in k in range of 2 plus k plus 1, right? Because we have already a preset case for 0 and 1 case, right? And then for each of the for each of the eggs, right? And then we also need to enumerate all the range, all the n's, right? From 1 to n plus 1. Okay, basically given like a case egg and nth floor, we want to choose like a floor, right? Between 1 to n. to try basically to drop this case egg. Okay, so that when we have like this kn is going to be the like I said, minimum of the dp of kn, right? Kn, then the so first one is the one we need to do a plus one because that's the current move, right? To drop the case egg. And then we have two scenarios. The first one is the egg broke, right? So if it broke, we have k minus 1 egg left, and then we need to go to m minus 1 floors to check, because like I said, we know the f will be in that range. Okay. And another one is that if the egg didn't break, then we know we have first we still have case egg left, and then the floors that's left is going to be n minus m, right? That's going to be the other part of these floors. And then in the end, we can simply return the dp of k and n, right? So it means that that's going to be the final queries for us. So run the code, accept it. Yeah. So I mean, in terms of logic, this thing works, but as you guys can see, it TLE, right? Because given like this kind of no, the constraints, right? So the time complexity for this one, as you guys can see, it's what? It's k times n square, right? So with this kind of constraints, this thing obviously it'll TLE. Yeah. So how can we improve that? So the way to improve that, is we have to basically look at this part. So when you look at this one, so we want to minimize for each of the k and n, right? We want to minimize this max value, the max between those two, right? So what does it mean? It means that we want to make sure these two values are as close as possible. Because let's say if we have 1 9, right? So the max of these two, well, of course, will be 9, right? I mean, but if we have 5 and 5, then the max value of this one will become to 5, right? So that's how we get the minimum, right? And so with this m here, right? So as you guys can see, so the first one is in the m. So if the m is increasing, right? So if m is increasing, the first part is also increasing, right? Because the bigger the m is, the bigger the value this one is, because the m is on the in the positive side. But for this one, I mean, the bigger the m is, the smaller the value is, because the m is the negative m, right? So since we have this kind of monotonical like increasing and decreasing, we can use a binary search to help us to improve this for loop into a log n time. So how can we do it, right? So assuming let's say we have this one, right? We have this this one is like the dp, right? dp of k minus 1 m minus 1, right? And we have another one which is the this one, right? This one is dp k n minus n minus m, right? So what we are trying to, so basically this one is a break case, right? This one is a not break case. Okay. So what we're trying to find is that we're trying to find, like, ideally we want to try to find like if there's a like intersection between those two values, right? Between those two lines. Otherwise, we want to find like an m, right? We want to find an m that can give us the those two values as close as possible, right? So it could be somewhere here and it could be somewhere here, right? That's basically that's going to be our approach here. So and which means that we can try to find the m that, and we can use a binary search. If the break is smaller, than the not break values, right? Basically, we're gonna increase the m, right? Which means that we're gonna move our left pointer equals to m middle m plus 1. Else, the right pointer will be m. So that in the end, we can simply use the either left or right pointers to update the dp of k and n. Okay, so I'll try to implement that one. Maybe I'll try to explain a little bit more here while I'm implementing it. So instead of using the for loop here, right, we can do a binary search. So we have L equals to 1 and right equals to n, right? That's going to be our search base. Like I said, so while L is smaller than L, and then we have middle. The middle will be the L plus L R minus left, right minus left divided by 2, and then we have break and not break. So the break will be the k minus 1, and then we have a middle minus 1, right? And the not break will be the dp of k n minus middle, right? Basically, if the b is smaller than not break, right? And then we'll do a L equals to middle plus 1. Oh, sorry, middle plus 1. Yeah. Else we do a R equals to middle, and then in the end, we can simply do this dp of k, the kn, right, becomes the minimum of the dp kn max dp k minus 1 l minus 1, since we have find the optimal indexes or the optimal m, right, either with equals to either L or R, so that we can use that one to populate that in the end. That's the break, and the not break is the dp of k and then n minus L, right? So of course we also need to do a 1 plus this thing, right? This can be this. Yeah. Yeah, so basically this will give us the same result. I mean, if I run it, but I just want to point this out here. As you guys can see here, basically we're trying to find out the first m where the break value is not smaller than the not break values, right? But I think this is not 100% accurate because since these two lines, right? So this break and not break, right? So this is the this is a break, right? This is the not break. Since these two lines are not continuous, so there's some like these discrete like values among those things here, among the lines here, because the first m could be here, second one could be here. There could be no like intersections with this two lines here. Maybe the next one could be somewhere here, right? If that's the case, but our logic here, it finds the first m, right? The first m that's the break is not smaller than the not break. So could have m1, m2, and m3 here. So when we're at m2 here, the break is still smaller than the not break, right? But the next one, right? The next one could be here. In this case, the break will be greater than the not break, and this is the ones we're using here. But I think to make this algorithm more accurate enough, after getting this out here, right? I think we also need to use the L minus 1 to check to compare with these two. Basically, I think we need to use two values to set this dp kn here, because so the first one, the first L is here, but we might the L minus one might give us a smaller values, just for example in this case, right at here, because the for this one the max value is 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 here, right? But for this one the max value is here, right? That's why maybe the previous one can give us a better result. So that's, I think, it's to be more accurate, we should use both the L values and L minus 1 values to populate this dpk and n. Right, assuming this L is greater than 1, of course, right? That's the boundary check. Yeah, so I think that's the binary search. If I run this one, unfortunately, even the binary search one will TLE for Python solutions. As you guys can see, now we have improved from 5,000. If you guys still remember, with the first solutions, it timed out at 5,000, but now we can handle 7,000, almost 8,000, but still timed out. So the reason being, it's not the reason being, because for this kind of approach, the time complexity obviously is k times n times log n, right? But still with Python, it's still timed out. But I think at this point, this one is good enough for most of the people. And the remaining of this video is optional to you guys. And cool. So if we still want to improve this kind of solutions, right? I mean, how can we further improve it? I think the way there is a way, that we need to redefine the DP functions here. So currently we have DP k and n, right? So the DP k and n means that with k eggs and n floors, we want to check what's going to be the minimum moves we need to make. So the way it works is that we should define like this. So with DP let's say DP I and j. Okay, so DP I and j means that with I moves, and j acts, how many floor it can check. Okay, so that's going to be the new definition for the new DP. So this thing means that okay, so like what I just wrote here, assuming we have I moves and then we have a j acts. So how many floors we can cover, right? And whenever the floor is greater, whenever the floor is the DP values is greater or equal than the n, then the I will be our answer. Okay, so basically we're trying to greedily include more floors given like the i's move and the j acts, and then the moment we can cover the entire floors, right? And then the value the current move will be our final answer. So because in that for that reasons, we have to loop through the outer loop has to be the moves. Basically, with the moves has to be from 1 to n, right? That's the outer loop has to be this one, so that we can greedily find the the answers, right, from 1 to n. Okay, so this kind of the definitions. So what's gonna be the state transition functions for this with this definition? So dpij. Let's say we drop this the j's egg, right? So again, right? So the j's to drop the j's egg, it has two scenarios. The first one it broke. The second one is didn't broke. Okay, so and of course the first one is 1 plus. So now this one means that we have already checked the current floor, right? So remember it's how many floors we want to check. So to drop the j's one, the first one is going to be since we have already checked the current floor, that's where it's 1 coming from. And then first, if this by dropping the j's egg, if it's broke, and then we need to go back similarly we need to go back to what to the I minus 1 and then j minus 1 floors. Okay, right? So remember now the dp this and this means that how many floors it can cover. With this now, since we have already used this x because it broke, right? Now we have the previous step will have like j minus 1 x left, and then the step will be I minus 1. Right, so that's going to be the x got broke case, and then the second one is the what is the not broke the broke scenario. It's going to be dp of I minus 1 and then j. Right, so this one means that we have used 1 moves. That's why we have I minus 1 moves left, but we still have like j x left. Then the question is that why we can summarize those two together here to get the total floors that we can cover, right? I mean, just think about the reason the definition of this dp I and j, right? Since we're trying to define this dp I and j as basically as many floors as many floors as we can cover, right? Even though we have two scenarios, right? Because if basically we have two possibilities here. The first one is the current x got broke, right? But the other side of this scenario is that if it didn't got broke, then we can use this same x to reach a higher floor, right? To reach a higher floor means that we need to plus that floor on top of the current one, because this one, the 1 plus dpi minus 1 and j minus 1 is the floor below the current below our current floor, right? And then for the case of the egg didn't broke, right? And then we need to basically add more floors on top of the current floor, because it means that we can check more floors in that scenario, right? So I mean, basically the key idea here is that we shouldn't assume cannot always assume the eggs always broke, because the again, right, the f is not fixed, right? So which means that the f could be here, it could be on this in this first part, but f can also be on the second part, right? We never know that. That's why we have to uh, basically we have to summarize those kind of two scenarios together so that we can get the total floors we can cover with with i's moves and then jx number of jx. Yep. So let me try to code that things here. So at the beginning, so now the definition has changed. So the default will be 0, right? So we have k plus 1 x in total for this thing in range of n plus 1, right? For I in range of 1, so k plus 1, right? Sorry, not k plus n plus 1. So the outer base, the outer space, the outer loop gonna be the moves, right? So at the most we need n moves, okay? And then the inner loop will be the number of the x we have here, right? K plus 1. And then like I said, we have dp of I, j equals to what? Equals to dp of I minus, 1 plus dp I minus 1 j minus 1 plus the dp of I minus 1 j, right? So that's going to be the total floors we can cover here, right? And then if the dp I and k, right, is greater than n, and then we return I. Yeah. So because we use the uppercase K here because we want to consider all the case X, right, for this ice moves. And if this thing is greater than n, then we know this I is our answer. So if I run the code, submit. So now finally it passed, right? Because as you guys can see now, the time complexity becomes to the n times k, right? Which is much faster. Big K here. Yeah. So actually, so here we already covered some of the scenarios here. Basically, the corner case will be, let's say, with zero floors, right? With 0 floors, and of course, we can cover 0 floors, but with 0x, we can also only cover 0 floors, right? So that's why we don't have to preset this kind of edge cases because we have already initiated everything with 0 here. Yep. So I think that's pretty much the everything I want to cover here. I know for the second part, this one, I know it's kind of hard to understand. So even I spend a lot of time trying to convince myself why we can use this kind of formula to represent this dp I and j, right? Yeah, just try to think about that. Maybe I'll give you another like fun induction for these things. Let's say we have two 2x, okay, 2x, and then we have n floors, right? So let's say we have a 2x and n floors. What's going to be the minimum the minimum moves we need to make, right? So that we can find that f within these n floors. So since we have 2x, right? So the question is that which floor we want to drop the first egg, right? So how can we find that? Because as once we drop that once we choose that floor, right, and then we can only assume the worst case scenario. Okay, the way it works is that let's say the let's say we place we chose case floor, the case floor to drop the first egg, right? And if it didn't break, if it broke, right? We need to use k minus one. We need to check the k minus one floors, right? Plus the current one, which is going to be the k value, right? Going to be the case floor of that. But if it didn't break, so what's going to be the next value, the next floor we want to pick, right? Assuming that we have okay, I think all right, so assuming this move, assuming this move is k, the minimum number of moves is k, right? So how can we find this k value? So basically the strategy will be what? Will be the first time we'll try to drop the egg on the case floor. On the case floor, so that if at case floor the egg broke, right? We still have a k minus one moves left, and with k minus one moves, it's guaranteed that we can check k minus one floors. That's why we chose this case floor as the first floor as the floor to drop the first egg, right? And if this egg didn't break, right? So if the egg didn't break, so which will be the next place we want to drop? So basically we have case floor, right? So now the next floor we want to drop is k plus k minus 1, right? So, and why is that? Similarly, like the previous one, let's say at k plus k minus 1 floor, right? Basically here, I mean, I can think of it like a k minus 1 because from here to here, I'm increasing k minus 1 floor. That's why the total floor is a k plus k minus 1. Because if at this k plus k minus 1 floor, it broke, right? And then we need to check k plus 1 to k plus k minus 2 floor. So here we have, this is a k minus 2 floors in total that we need to check, and this one is exactly to our current remaining moves, which is the k minus 2. So that if we jump an k minus 1 floors, even though this thing broke, we still have enough moves that can cover the range from the k to this k minus 1, k plus k minus 1 floor, right? So again, if this thing didn't break, then we'll jump to another one. So basically, we'll jump to with a k minus 2 floors with the same reason, right? And then as you guys can see, so basically every time we jump from case floor, we jump k minus 1, and then we jump k minus 2 until we jump to 1. Okay, so what's gonna be that result, right? So it's gonna be a k plus k minus 1 plus k minus 2 plus until 1, right? So what's this things here? It's a 1 plus 2 plus 3 plus k, right? And then this thing will be the k times k plus 1 divided by 2. So, and we want to make sure this one is greater than n, right? And that's how we get can calculate this k here, right? Yeah, and yep. So I think with this thing, I think it's not that hard to calculate what is the value for k, right? Actually, so there's a even like more generic version of this formula here. Now we have the x is equal to 2, right? So what if we have mx here, right? So what's gonna be this formula? So it turns out the formula will be the m factorial in this case, and this will be the formula, right? And we can use this formula to also find the k values. I'm not going to go into details how we get these things, but I think basically that's how this formula works. Uh, cool. I think I have talked uh, enough, discussed enough about this problem. So I hope you guys like these videos, and I guess I'll just stop here. And thank you for watching this video, guys. Stay tuned. See you guys soon. Bye bye.